Okay. I'm recording this, so a lot of these announcements aren't for you. You already know about them, but for the other two guys, just so they'll know if they ever listen. Okay. This week is the end of first mini-term. I'm giving my final in my first mini-term class this afternoon. Then next week begins the second mini-term. So we're right at midterm. And usually, shortly after midterm, as in Wednesday of next week, we have to do a midterm progress report. You're in good shape. You've already turned in your first test, done quite well on it. So nope, I don't have to turn in anything on you. They only require this for people who have D's and F at midterm. And I don't have my projector plugged in. This has been one of those days. Usually I do this when I first come in, but I have that student here and I was trying to get other things done and I completely My wife can tell you one of my personality traits is I'm staid and rule bound, and if something goes out of order, it doesn't throw me, but I don't get things done the way I need to. All right, let's get my pen set up. Okay, so back to the announcements. So by next Wednesday, I have to report anyone who doesn't have it's not passing at midterm. It has D or F at midterm, so just know that's coming. Volleyball team, today's the 10th, right? Yeah. We'll be going to a tournament up at Wallace State, Hessville. That will be tomorrow and Saturday. So if you happen to be anywhere close to Hessville, stop in and cheer the team to victory. Okay, I'll do the rest of those next time. Today, from 1 to 3:30, which you will have time after this class to go to if you're interested, is the Scholarship Summit Fall 2019. And that is on this campus, faculty staff dining room, which is just next to the cafeteria, from 1 to 3 o'clock this afternoon. The Scholarship Summit participants include Alabama A&M, Alabama State, UAH, Birmingham Southern, Jacksonville State, Tuskegee, Miles, University of Alabama at Tuscaloosa, UAB, Mercer University over in Georgia, Samford University here in the local area, University of West Alabama, North Alabama, Mississippi State University, and University of South Alabama. So that's today from 1 to 3. It was yesterday on the Birmingham campus, today on this campus. Okay, and one last, you've heard it, and it's coming up to almost be said, but more, I will go over it one more time next week. The NASA Community College Aerospace College Program will be accepting applicants for this new year, school year, up until October 16th. That's next Wednesday, 1 week from yesterday. So that's the end of that. Now, on my personal level, normally I'm here till 6 o'clock on Tuesdays and Thursdays. However, today is the last day for that mini-term class. All they've got to do is the final today. It will not take them 4.5 hours to do their final. It's not that hard. Okay, so I will probably be leaving a little early. If I can get away by 4, I'm going to try to do so. So I won't be here till 6 today like I normally am, but I'm normally in class until 5:45. So I will be leaving a little early, and I'm taking leave tomorrow. I will not be on Birmingham campus at all tomorrow. We've got to go out of town, and so I will not be there. Okay. What else? I guess that's most of what we've got. So let's go on and get started on where we left off last time. We just got, no, let's see. yeah, we hadn't started elementary matrices, had we? 2.4? I didn't think so. I didn't remember it, but I had a mark on the next page. I think all we did, we finished 2.3, right? Yeah, okay. So we're starting 2.4 today. Now, now 2.4 is a bit long. If we do finish it today, that is the last. No, there is 2.5. So we're not going to do much in 2.5. So if we finish 2.4 today, I will try to run off copies. Well, I have to find to see if I have an electronic copy of the test so I can run it off for you. But if I don't, I got to make it up, so that'll be next week before that happens. But if I can, I'll try to do it today. But I don't know if we'll finish 2.4 or not. Any questions on anything we've done so far? Okay. All right. 2.4 is talking about elementary matrices. Okay? So, here is what an elementary matrix. Well, first, you got a book, right, or electronic book? Okay. Section 1.2 introduced the 3 elementary row operations for matrices, and what were they? Changing any 2 rows, multiplying any row by a non-zero constant. That's either multiplying or dividing by a non-zero constant. And the third one, adding a multiple of 1 row to another row. Those are the 3 activities you can do, and you produce what they call equivalent matrices. Okay, same solutions, that kind of stuff. Now, I'm sorry, my throat is all froggy, so I'm having trouble talking clearly. In this section, you'll see how to use matrix multiplication to perform these operations. Okay? Those were your Gauss-Jordan operations. Now we're going to do it, or show you how to do it with matrix multiplication. And you might think, wow, that's a lot more difficult. Well, there is a reason, and it's coming up, but it doesn't manifest itself till the end. So first, we're going to talk about what an elementary matrix is. So the definition of an elementary matrix, I'm going to write this on here even though I know you've got it because some may not have books. Elementary matrix is an n by n matrix, okay, n by n. Now notice by that statement there, they have to be square. An n by n matrix is an elementary matrix when it can be obtained from the identity matrix I sub n, okay, by a single elementary row operation. Okay, those 3 things we just said. Exchanging 2 rows, multiplying or dividing a row by a non-zero constant, or adding a multiple of 1 row to another row. But you do that to an identity matrix. So it's pretty easy to identify an elementary matrix. It's just had 1 elementary row operation done to it, and that's all. Okay? So, example 1 lists several matrices, 6 matrices there, and we are to determine which of these are elementary. Okay? Can you read them off yours? Okay. The A one, I'll not write them down, but just read it. 1, 0, 0, 0, 3, 0, 0, 0, 1. Is that an elementary matrix? Why? Okay, you just multiply the second row by 3. That is a single elementary row operation, so this is an elementary matrix. How about B? 1, 0, 0, 0, 1, 0. Why not? It's not square. An elementary matrix has to be square because you've operated on an identity matrix, which has to be square. Number C, 1, 0, 0, 0, 1, 0, 0, 0, 0. Is that an elementary matrix? Why not? Only way you could have gotten it was multiplying the third row of the identity matrix by a 0. And you can't multiply by 0. Remember, you can multiply by any non-zero constant. So C is not an elementary matrix. How about D, which is 1, 0, 0, 0, 0, 1, 0, 1, 0. That is. Why? Yes, you exchange rows 2 and 3 to get this. A single elementary row operation. Number E, 1, 0, 2, 1. Is that an elementary matrix? Why? Okay. Absolutely. You multiply the top row by 2 and added it to the second row. Perfect. And F, 1, 0, 0, 0, 2, 0, 0, 0, negative 1. Why not? Yes, that required 2 elementary row operations, not 1. You multiplied the second row by 2 and the third row by negative 1. That's 2 elementary row operations. An elementary matrix can only have 1 elementary row operation done to an identity matrix. Okay, perfect. Now, so what's the big deal about them? Elementary matrices are useful because they enable you to use matrix multiplication to perform elementary row operations, as demonstrated in example 2. Well, my question would be, why would you want to? But it does enable you to do it, and we'll see later why. And once we've done it, you'll still say, well, why did we want to do that? But it does enable something to happen that's pretty unique, okay? Now, here is an elementary matrix. 0, 1, 0, 1, 0, 0, 0, 0, 1. Do you agree that is an elementary matrix? Yay or nay? Why? Yeah, you exchange the first and second rows. So that's a single elementary row operation you did to a matrix. So we're going to call this E for an elementary matrix. Okay? Here is a general matrix A. 0, 2, 1. 1, negative 3, 6. And 3, 2, negative 1. That's sub-arbitrary matrix A. All right. What happens when we multiply those two together? You form a 3 by 3. First entry would be 0, 1, 0. So that's 1. Next entry would be 0, minus 3, 0. That's minus 3. Next entry would be 6, 0. Okay? So that would just be 6. Second row. First entry would be 'Okay. The 2, 1 entry. Second row, first column. 0, plus 0, plus 0. So that's a 0. All right. 2 entry, second row by second column, 2 plus 0 plus 0. That's just a 2. The third entry on the second row would be 1 plus 0 is 1. The third row, first entry, would be 0, 0, 3. Next entry would be 0, 0, 2. And third one would be 0, 0, minus 1. Now, compare these two matrices. Matrix A with what's on the other side of the equal sign. Do you notice anything? Yes, you exchange the first and second row. Third row stayed the same. The first and second row is exchanged.
Thank you so much. And I'm gonna get back with you on the lab. We'll try to get the labs and the paper done as we can.
Okay.
And just scan it to you, whatever.
Okay. All right.
Okay.
Thank you so much.
Okay. Now, thank you for being so kind to me.
All right. Okay. All right. Yes, the very thing that you did to the identity matrix to get this elementary matrix was the very thing that when you multiplied it, it did to matrix A. It exchanged the top two rows, that exchanged the top two rows. So this enables you to do any row operation, any elementary row operation you do on the identity matrix, that will be the same one done on matrix A when you multiply the product. Okay? Now, let's see if we can do the B part here too. They claim this is an elementary matrix. 1, 0, 0. So far, so good. 0, 1 half, 0. We'll hold that and see 0, 0, 1. Is that an elementary matrix? What do you think? Yes, it is. Okay? And what we're going to operate on is this. 1, 0, negative 4, 1. 0, 2, 6, negative 4. And 0, 1, 3, 1. Okay? Let's do that to that. Okay? Now can you even do that multiplication? Yea or nay? Yeah. 3 by 3 by 3 by 4 is going to give us a 3 by 4, so we're going to have a 3 by 4 here. Okay? First entry would be 1. Next entry would be 0. Next entry would be negative 4. And next entry would be 1. All right. The 2, 1 entry. Second row, first column. 0, 0, 0. So that would be a 0. 1, or the 2, 2 entry would be, you say 1? Perfect. Next. 3. Next. Negative 2. All right. Third row. Third row, first column. 0. Third row, second column. 1. Third row, third column. 3. Third row, fourth column. 1. All right. Now notice what happened here. First row, third row, not a thing happened. Second row, though, divided by 2, which is exactly what you did to the elementary matrix, to the identity matrix, you get that elementary matrix. That's what you did to this matrix when you multiply. So what that is saying to you, the elementary matrix, whatever operation you did to an identity matrix to it does to the matrix you're multiplying, as long as the multiplication is legal, and it is in that case. So let's go to C down here. I'm going to have to erase, goodness gracious, my head's so clogged up I can hardly breathe. Shouldn't be making all these noises. People won't listen. Okay. Here's a 1, 0, 0, 2, 1, 0, and 0, 0, 1. It's labeled as the elementary matrix. Is it? Why? And add it to the second row. Perfect. You just did a single elementary row operation to the identity matrix, multiplying the top row by 2, adding it to the second row. That's all you did to get this, so that's an elementary matrix. So we're going to multiply this by, some other matrix A, and this is 1, 0, is that a negative 1? Yeah. Negative 2, 3. And 0, 4, 5. Okay. 3 by 3 by 3 by 3 is going to produce a 3 by 3. Okay. All right. First entry will be 1. Next entry will be 0. Next entry will be negative 1. All right. Next entry would be, okay, the 2, 1 entry. That'll be a 2, right? Okay, minus 2, 0. Yeah, you're right. 0. Perfect, sorry. Next. You may have said it right, I just don't hear well. Negative 2. Okay, got it. Okay. 0 minus 2, yeah. And next entry? One, okay. Motorcycle, whatever, went by and I couldn't tell if you said anything or not. And the next entry would be 0. Did you say 4? And 5. Okay. Now, this one is not quite as easy to see what happened. But let's see if we can figure that out. Okay. Top row stayed the same. Well, a couple of times we have the board clean, and so far it's not. Okay. Top row and third row stayed the same. Something happened here. Okay. It looks like we did a row reduction. Multiply this by 2 and add there. Multiply this by 2 and add there. Multiply this by 2 and add there. Sure enough, that's exactly what happened. Okay? Which is what happened here. Multiply this top row by 2, add it to the second row. So sure enough, we use that elementary matrix on this matrix A, it does that operation that you had done to E, did it there. Now, you might say, why do you do this? Well, as you just saw, doing that elementary row operation to A wasn't hard, but there was more involved with it. To do it to an identity matrix is a piece of cake. I mean, you just change one number, and that's all, okay? So that's so easy. And then multiplying these, the top and bottom rows don't change a thing, and that next one's a pretty easy operation to do. So in reality, it's almost as easy as a Gauss-Jordan elimination. A little more writing, but it's still a pretty easy thing to do. Okay, calculationally wise, it's pretty simple. Now, it says, excuse me, notice that in the product EA, 2 times the first, oh yeah, we already said that. All right. In each of the 3 products in example 2, you're able to perform elementary row operation by multiplying on the left by an elementary matrix. The next theorem, stated without proof, generalizes that property of elementary matrices. All right. Let E be an elementary matrix. Okay. Obtained by performing a single elementary row operation. I'm going to call that ERO, elementary row operation, on an identity matrix of the appropriate size, I sub n. M. Why they change from N to M, I don't know, but they do periodically. Okay? I think that's the period there. If that same elementary row operation, ERO, was performed if the same elementary row operation was performed on an M by N matrix, A, then the resulting matrix is given by the product Ew, goodness gracious. Is given by the product EA. Okay, always multiplying the elementary operation on the left to the matrix in question. Okay? Now, they say if you had multiplied on the right, then you would be dealing with right multiplication of elementary matrices. Really, at one point, thought it was going to be best to just be able to go either way. No, you can't. To do elementary row operations, always multiply with the elementary matrix on the left. If you're going to do column operations, that'd be on the right. This book isn't going into that. So most applications of elementary row operations require a sequence of operations, not just one, not just a single one. For example, Gaussian elimination usually requires several elementary row operations to reduce a matrix. Yeah, we remember that. That translates into multiplication on the left by several elementary matrices. And the order of the multiplication is important. My head hurts. It hurts to read. That translates into multiplication by several elementary matrices. The order of multiplication is important. The elementary matrix immediately to the left of A corresponds to the row operation performed first. And that's what example 3 is going to show. All right, so let's go to a clean page here. Oh my goodness gracious. I think part of my, I don't know what it's causing this, but I did cram down lunch awfully fast. I wonder if that's got something to do with it. Okay, because I had very limited time. I had students in and out constantly. All right, so find a sequence of elementary matrices that can be used to write the matrix A in row echelon form. Notice row echelon form. Not reduced row echelon form, but row echelon form. Okay? Here's your matrix A. 0, 1, 3, 5. 1, negative 3, 0, 2. Got it. Goodness, I was trying to space these out well, and they didn't agree. 1, negative 3, 0, 2. I'm sorry, my throat is just closing up on me. Okay. 2, negative 6, 2, 0. Okay. Now,
Yeah, that's all.
yeah, for, oh yeah, T27. All right, take care. Have a good weekend. Okay. Now, they do it this way, and it's perfectly sort of okay to do this way, but frankly, I prefer, they just said multiply on the left, and you got to, okay? So when they do this, they put the matrix on the left and put the elementary matrix on the right. And it's okay. I mean, you're not multiplying them, but why not put them where you would be multiplying them anyway? I don't see the reason for that. To me, it's okay. Well, here's how I would do it. If I hope you don't mind if I modify this a little bit. Okay, what would be your first step to row reduce matrix A? What would you do first? Yes, exchange 1 and 2. So what I'm going to do is write down the elementary matrix. I'm going to call it E1 that does that. Or you tell me what to write down. What elementary matrix would swap the first 2 rows? 0, 1, 0, 1, 0, 0, 0, 0, 1. That sure should do it. Okay? And the new matrix A that would come out of that, and this may be part of the reason, you would be doing that to the matrix up there, and you would get the matrix down here. What would that be? Like you said, just swap the top 2 rows. 0, 1, 3, 5. Now, I'm not multiplying it, but I'm telling you that's what you would get out of it. Okay? And then the bottom row stays the same. 2, negative 6, 2, 0. Okay? That's all you did. Swap those 2 rows. This is the elementary matrix. We operated on that. We give you that. Okay? Now, what would be the next thing you would do? Okay, multiply row 1 by negative 2, add it to row 3. So what would that give you as the elementary matrix if you had done that? Top row stays 1, 0, 0. Middle row stays 0, 1, 0. And the bottom row becomes negative 2, 0, 1. Okay? When you multiply the top row by negative 2 and add it to the third row, if you did that to an identity matrix, that's what you would get. Right? All right. And if you did that to this matrix, then the result would be 1, negative 3, 0, 2. It's an ugly negative 3. Okay. Zero, 1, 3, 5. Okay. Yuck. Okay. All right. Doing what you just said. Negative, we're doing both of them. Well, we're not really multiplying, but let's do that row operation. Negative 1 and negative 2 times row 1 added, no, to this one, yeah. Sorry, looking at the wrong one. Added to row 3. What would that give us? 0, 0. And what? 2. Negative 4. Okay, got it. Now, what's the next thing you would do to this one to try to row reduce it? Okay. Yeah. Now, as I said, row reduce it, not. Wait. Yeah. Elementary row operations. Let's see. Am I using my terms right?
I know what you
Yeah.
mean.
You're not getting that to change.
Yeah.
Just this. Okay. All right. And what do you say it was? Okay. And what elementary matrix would do that for you? 1, 0, 0, 0, 1, 0, 0, 0, 1 half. Divide by 2. And if you did that to this matrix, then your product would be 1, negative 3, 0, 2. Top row stays the same. Middle row stays the same, 0, 1, 3, 5. Bottom row becomes bottom row becomes 1, negative 2. Okay, pretty ugly over there, but that is your new. Now you have this in row echelon form, not reduced row echelon form. I kept trying to get a reduced in there. I didn't need a reduced in there, okay? And let's see how we compare to what they have. Yeah, the third matrix is that. All right. Now, so this matrix that we wind up with here, we're going to call, or he's going to call B, okay? Now, rather than doing one at a time, you could have just said you did E3 onto E2 onto E1 times A, and that produced B, okay? Now, they wrote them in different order. B is equal to E3, E2, E1, A, which I guess is, for some reason, they prefer to write it that way. Don't really see that it would. Now, and they write down these things without and they put a little remark here. The procedure demonstrated here is primarily of theoretical interest. In other words, this procedure is not a practical means by performing Gaussian elimination. Just noticing you could do it that way, okay? And that's what you would do. With these 3 E's that we've identified here, you can get it into a row echelon form. Not reduced, but just row echelon form. This thing, I'm getting so sick of this. Now, you could multiply those out and do them. I think we're both convinced it will work, so let's not, okay? Now, these are row equivalent matrices. A up here and B over here. Those are row equivalent. In other words, they're equivalent matrices. And B is the product of those 3 elementary matrices times A. Now, the definition of row equivalent matrices is restated using elementary matrices as follows, so let me go on and write that down. Again, I know you've got it in your book, but maybe not, excuse me, everyone at home does. So A and B are M by N matrices. Okay? Matrix B is row equivalent to A when there exist, I don't know why it writes and then disappears, there exist a finite number of elementary matrices E1, comma, E2, comma, E3, comma, dot, 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 up to and including E sub k, some finite number, we don't know what it is, such that B is equal to E sub k times E sub k minus 1 times E sub k minus 2, dot, 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 down to E sub k right, I'm sorry. Just start numbering these down because you're at the end. E sub 3, E sub 2, E sub 1 times A. Okay, whatever. They didn't list as many as I did, but it's okay. Now it says, you know from section 3.3, of course you remember that not all square matrices are invertible. Every elementary matrix, however, is invertible, okay, because it came from an identity matrix, and the identity matrix is invertible, so any elementary row operation on that will also produce an invertible matrix, okay? Moreover, the inverse of elementary matrix is itself an elementary matrix. So that leads to the next theorem. Okay. If E is an elementary matrix, okay, then E inverse, I'm sorry, I got lost on where my theorem was, exists. Okay, if E is an elementary matrix, it's by therefore certain to be invertible. So E inverse does exist and is itself an elementary matrix. That's supposed to be an elementary matrix. Okay, they're just telling us that it will be the case. Okay? Now, the inverse of an elementary matrix E is the elementary matrix that converts E back to I sub n. So you really have to do some backtracking in your mind now. Okay? So let's look at those. Okay? Here was E sub 1 that we got before. It was 0, 1, 0, 1, 0, 0, 0, 0, 1. All right. What did you do to the identity matrix to make this happen? Row 1 exchanged with row 2. Okay? Now, how do you think you get it back? Just do it again. Just swap them back. So this would be the elementary matrix that would do that, that would swap those and get them back in the thing, would be itself. 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay. Okay. Where did it go? It just erased itself. I don't know why. Okay? So, sorry about that. E1, I'm going to have to write it down again. That's the E1. My pen is dragging now. Nothing seems to be working very well today. E1 that we used before was 0, 1, 0, 1, 0, 0, and 0, 0, 1. You got that from interchanging the two rows, R1 interchanged with R2. And then how you get it to go back is exchange again that 1, 0, 0, 0, 1, 0. That's a 1 and that's a 0. Goodness gracious. Okay. Let me start over. There. All right. To get this to go back to the identity matrix, you exchange the two rows again. So the new elementary matrix, E1 inverse, would be 0, 1, 0, 1, 0, 0, 0, 0, 1. You just flip the two rows again. What you did here, you do here. And that gets you back to the identity matrix. Okay? Now that almost feels like we're running around in a circle here. And we are coming close to it, but not quite. This one, that's all you're doing. It really feels like you're on a treadmill here, and you just turn it around. But let's go to the second of those. E sub 2, the second one we used was 1, 0, 0, 0, 1, 0, negative 2, 0, 1. Okay. Remember, the next thing we did was multiply the top row by minus 2 and add it to the bottom row. That undid our that's what you did to the identity matrix to get this, and that's what we did to the what was remaining of the A matrix to get to the next step. Okay? Now, how do you undo that? Okay? How do you get this thing to go back to being an identity matrix? Okay? You would do top row by 2 and add it to the third row. Okay? So what would be the elementary matrix? So what we did here, this was done by doing minus 2 row 1 plus row 3. I can't write. Becomes a new row 3. How you undo that is two times row 1 plus row 3 is the new row 3. So that would be a 1, 0, 0, 0, 1, 0, 0, okay, you're doing it to the elementary matrix, so that would then be a 2. Zero, 1. All right. And you see that's indeed what they did. It's what you have to do to this to get back to an identity matrix. We'll multiply this by 2 and add it to this row. And that's what you do to the identity matrix to get that. So this is E2, E sub 2 inverse. Okay? Now, the next thing we did was E sub 3. The elementary matrix there was 1, 0, 0, 0, 1, 0, 0, 0, 1 half, right? Multiply the third row by that. So how do you get this thing to go back to being an identity matrix? Okay? These two rows are fine. Just multiply this one by 2. Well, if that's what you had to do, then the elementary matrix that does that for you, so this is what we did was row 3 divided by 2. Goodness gracious, this is so what a pain in the neck, is the new row 3. That's supposed to be a 2, okay. So what you do here to get it to go back is a 1, 0, 0, 0, 1, 0, 0, 0, 2. That's your elementary matrix. Inverse elementary. E3 inverse, okay? The elementary matrix that takes this one back to being the identity matrix, you just multiply the third row by 2, which is in itself. So this would be R2, R3 becomes a new R3, okay? So now, the elementary matrix that undoes the exchanging 2 rows is just exchanging the same 2 rows back again. Okay, so the elementary matrix and its inverse are identically the same for that case. For adding a multiple of one row to another row, you do that to the identity matrix to get this, and to undo this, you multiply the opposite of this one to the same first row and add it to the third row. Okay? And then to this, when you're changing to get to a half down here, when you're dividing by 2, what you do here is multiply by 2. So this is just an exchange. This is an exchange with an additive inverse, and this is an exchange with a multiplicative inverse. That's one way you can think of it. I don't know if that's easy to remember, but the easiest thing is how do you get from here back to an identity matrix? That would give it to you. All right. Now, I thought I left my watch up here, but I didn't. It's in my pocket. How are we doing? Can't hear. 6 minutes left. I thought we were getting close. I don't trust myself now. Yesterday, I met with a class, and because Corey had a long way to go from here, we started the class 15 minutes early. And so we got going on it, and he had to leave sort of early, but it's the same 3 students in both of those 2 classes yesterday. And one of them ends at 5 till, the other one was supposed to end. Let me see if I can remember. At quarter till on the next hour. And we started early, so that was going to be ending at 1/2 And when we got to going, we'd been going, great guns and stuff. And then when he left, I happened to look down and saw, oh, it's almost 5 till. We're almost through a class. So I hustled up and finished it. And then the others didn't say a word to me. The 2 others didn't say a word. And when I got to my office, I said, wait a minute, it's way too early. Rather than doing 15 minutes early, we had finished 30 minutes early. And that was bad news. I got all screwed up in the head. So I don't want to do that to you, and I've just talked away several minutes. Sorry about that. So let's do theorem 2.14. At least we'll get this done before we're through. A property of invertible matrices. A square matrix A, okay, is invertible if and only if, that symbol means if and only if, it can be written as a product of elementary matrices. Let me write them out. Elementary matrices. Okay. Now, earlier we had other definitions of what is an invertible matrix. Here's a new one. A square matrix A is invertible if and only if it can be written as a product of elementary matrices. Now, example 4 is example 4 is a 2 by 2. That shouldn't be too hard, should it? Oh, maybe it is. Okay, because it's not a trivial one. Yeah, this is going to be longer to do than what we have time. So we'll start next time with example 4. Sorry about that. Homework exercises here would include any of the odds this is on page 82 and following. Any of the odds 1 through 7, they're all found at Calc Chat. 9 or 11 are found at Calc Chat. 13 or 15 are found at Calc Chat. (17 through 21 are found at Calc Chat. And we'll pick up with 23 next time. All right. Good deal. Okay. One reason needing to do a little early is I've got to go off campus for just a moment before my next class starts, so I couldn't run over today. So sorry if you felt cheated out of some of your tuition dollars, but you're very kind to forgive me on that.